Thank you very much, and I want to thank the organizers for the invitation. It's great to be here in Hamburg again. It's a lovely place. So I wanted to use these 25 minutes to tell you as much as I can in this short time about my research in mathematics of quantum field theory. Okay, so first I want to tell you about the approach I'm using, so basics of the framework, and then I want to present some results on the Sine-Gordon model. So hopefully this all fits in time. Right, so what I'm working on is relatively new framework, which however is inspired by something which is much older, namely algebraic quantum field theory. So this was an idea, which is maybe 60 years old by now, to try to characterize quantum field theories, try to formulate mathematical framework for studying quantum field theories using the notion of observables as the primary object. So the idea goes back to Hagen and Kassler, and the basic gist of it is that the model of a quantum field theory should be in the first place defined by assigning to bounded regions of spacetimes, which tell you about localization, algebras of observables that you can measure, that you can localize in these regions. So to every region, we assign an algebra. Okay, so it's not very complicated. And there is some consistency condition. So if you have a smaller region inside a larger region, then you expect that if you go to the larger region, you don't lose observables. So this is then described as an isotony axiom. So the larger region has a larger algebra, so to say. Okay, and you can write it this way. You can also formulate it in a more modern language as a functor between certain categories, but at the moment, I don't want to go too far into this. And there are also some nice properties which are physically motivated, which we can ask this model to fulfill. So there are two which I want to mention. So first is causality, and the second is time slice. So causality has something to do with Einstein. So Einstein tells us, right, so we have two regions which are space-like separated, so information cannot travel faster than light. Everybody knows that. So if we make measurements here and measurements there, these are space-like, we want them to be independent. And in quantum theory, you say independent by saying the corresponding algebras of observables should commute. So the operators commute, you can do measurements independently. So this is written here. So that's causality. And the second property is time slice. So what does it say? Well, if we have a Cauchy surface in a given region, so if we have a space-like codimension 1 surface, which intersects with each causal time-like curve exactly once, then, okay, Cauchy, why Cauchy? Because classically we would write Cauchy data on a Cauchy surface, and in some nice class of PDEs, one could recover solutions of the PDE using the Cauchy data. So here we want to have abstract quantum version of that. So we say we give algebraic data in the neighborhood of the Cauchy surface, and this should give us the algebra of the whole region. Okay, so you can think of it as this structure being locally constant in time direction. So note that we are working in Lorentzian geometry, so there is a difference between time direction and space direction. So this is reflected in algebraic properties. So here you see that something special happens at space-like separation, something special happens at time-like separation. Okay, so this is what I just said. Now, perturbative. So AQFT is old, PAQFT is a bit newer. So constructing models of algebraic quantum field theory is terribly difficult, and well, okay, but we know that we have quantum field theories which work, but in order to construct them, one needs perturbation theory. So perturbative algebraic quantum field theory is to take this idea of locality, so this characterization of theories by algebras of observable, but allowed to use perturbation methods to construct them. Okay, so I would say it has the best of two worlds, so this has some sort of mathematical framework to talk about quantum field theories, but on the other hand, you use results which you know from perturbative QFT, and there are plenty of examples. Examples are great. Right, so let me just mention a few names, and I will use that as an excuse for telling you what are the basic mathematical tools that one uses in that context. So, first, deformation quantization. In the first step, one defines a non-commutative product. There was already some talk about deformation quantization in this conference. So, the first step, you construct some Poisson algebra and then use deformation quantization to get some non-commutative algebra. So this works. In this context, this was developed by these three people, Deutsch, Fenhagen, and Brunetti, in various configurations. Finally, they managed to write a joint paper. And okay, so this actually lets us deal with free theory. Free theory is relatively simple, but of course boring, because what's really interesting in QFT is the interaction. So for interaction, you need renormalization. And for this, we use a toolbox which was provided by Epstein and Glaser. So this is a more rigorous approach to renormalization, which works well on curved spacetime. So it works on a general class of Lorentzian manifolds that we actually want to apply it to. So yeah, but these methods are there. And well, okay, so of course you want to describe gauge theories as well, and embarrassingly enough, the first serious attempt to do that systematically came in 2007, so very recently, by Stefan Holland. He constructed an example, and then the general framework was developed by Klaus Frenhagen and myself in 2012 and 13. I will come back to that in the next slide. If you're still interested, well, there is a review book which has the same title, Perturbative Algebraic Quantum Field Theory, and, well, you can easily find it, I guess. Right, so let me just say about recent results. So this was all historical introduction. There is this thing with using Battle-Wilkowinski formalism, which I just mentioned, to describe gauge theories. So this was quite recent, and it opened up like a new door for algebraic quantum field theory. So now, okay, first we can use perturbative methods, that's great. And with BV formalism, we also realized, we can use homological algebra, which is even better. So slowly we are getting more and more abstract. But to get a bit more concrete, at the same time, we applied that framework to concrete models. So first we tried out the bosonic string, and then we tried out effective quantum gravity. So it works as it works, so one still has to deal with perturbative series, but it was a nice exercise to see that actually the framework is robust. And okay, quantum gravity, the natural next step is to use it to cosmology. So this was also recent work where we try to explain cosmological perturbation theory using these methods. And last but not least, we applied that to the Sine-Gordon model as well, where surprisingly enough, well, maybe not surprisingly, but still we managed to do it quicker than we thought. We found out that actually this perturbative series that one writes down converges very nicely, and one obtains a rigorous model. So I don't know if this makes you happy. It makes me happy, because there's not so many rigorous models on the market. Right, but let me just now concentrate on that last example and try to say something concrete in the remaining 15 minutes. or 14 minutes, I don't know, that you're more precise. So let's fix some globally hyperbolic Lorentzian spacetime. If you don't want to be bothered about globally hyperbolic, then think of Minkowski spacetime. This is a good thing to think about in your favorite dimension. Now, on this, we consider the space of smooth functions. So remember, we want to talk scalar field. And for free dynamics, the equation of motion is just the Klein-Gordon operator. And because of some sign convention, it's a minus Klein-Gordon operator, but it doesn't matter. Okay, so what do we know about it? It's a great equation from the point of view of PDEs because it has green functions with special properties. It has unique green functions which satisfy certain support properties. So there is retarded green function, which when it is applied to a test function f, it extends its support to the future. And there is advanced green function, which extends support to the past. So there is nice causality property to these solutions. And the difference of these two guys is called, sometimes misleadingly, causal propagator. This is not the best name for it, but somehow it got stuck in the literature. And what do we use it for? We use it as essentially as a bivector to construct a Poisson structure on the space of functions, on the configuration space. So let me just come to this now. So we define a Poisson bracket using the prescription of Pius, so that's why it's called Pius bracket sometimes. So given two functions f and g, we differentiate them both and contract with that bivector given by the causal propagator. This is a constant bivector, so this is actually a constant Poisson structure. And constant Poisson structures can be relatively easily deformed, so we define a star product as the deformation of that pointwise product by using the well-known Moyal formula. So we could take here delta, so our Poisson bivector, and then exponentiate it, contract with various derivatives of functions. But we don't do it. We don't do it from various reasons. So main reason is some analytical properties of delta which are not so great. And I was growing up as an analyst, so I still care about these things sometimes. But no panic, because actually we can always add something symmetric to our original bivector. So we have some bidistribution, which is totally anti-symmetric. We add something symmetric, so it's still, if we then modify that in the Moyal formula, it still gives the deformation quantization, which is equivalent to the original one. So that's why here I will always assume, or actually use the result, that there is a nice symmetric part that one can add to this, and one obtains a very beautiful star product. So this W has to be positive, definite as a distribution, and as I said, H is symmetric. Okay, so this is the free theory. So we assign to bounded regions of space-time, we assign this, for now, formal star algebra. Star because there is an involution given by complex conjugation. Okay, so free theory. Now, if we want to introduce interaction, we need to do a bit more work. So first, because I have very limited time, I will simplify things a lot. So let's take a space of very nice functions on the configuration space, which are regular in the sense that if I take a derivative, I get something smooth. So all the analytical problems are shoved under the carpet. Okay, so this is going to be fixed for the next few slides. So we take such class of nice regular observables, and on these we can define another exponential operator, which I call T, which looks very much like what we had before with the Moyal product. But here we use a byte distribution which is symmetric and which is called Feynman propagator. This is the same Feynman propagator as the physicists are talking about. And formally, okay, so we are finally talking quantum field theory here. So formally, applying that T would be the same as convoluting with the Gaussian measure. So if you know path integral, this is exactly the same as taking path integral of your observable, integrating over one of the entries. Okay, so that's the intuition that helps. And now we use this operator to define a new commutative product by twisting our original pointwise product of the classical theory. So this product is called time-ordered product because it has a beautiful property with respect to the star product. So it is the time-ordered version of that non-commutative product. So these are equal if the support of F is later than the support of G. Remember that all our observables can be localized somewhere, so they have places where they live, and we can say if they are space-like or time-like or what's the order. Right, and again, what is it good for? We can use it to define the S matrix. And the formula is really simple. We just take the time-ordered exponential with respect to that funny commutative product. And the interacting local fields are then given by a slightly more complicated formula due to Bogolyubov, which is also motivated physically. So this is like a very algebraic version of the formula for the Dyson series. So if you unpack it, then you find out that, oh, this is nothing else but the Dyson series. But maybe you don't see it at the first glance. And this object here, which is constructed from such time-ordered exponentials, is the interacting field. So given an observable, you can construct the interacting observable using this recipe. Right. Now, there is a catch. This was all algebra, but if you want to extend this whole story to things which are less regular than what I assumed, you need to renormalize. But again, my time is running out, so I won't be able to renormalize anything. And fortunately enough, there are models where you don't have to. So what I want to tell you about the Sine-Gordon example, this is an example where you don't have to renormalize anything under certain assumptions, and things work as nicely as I presented it. So you do very minimal functional analysis, and the rest is algebra. And everything which is algebra usually works out well. Okay, so, right, so what do we have? So the space-time is two-dimensional Minkowski, one space, one time, and the field is massless, so the operator is just minus D'Alembertian. Simplifies things greatly, so these retarded and advanced green functions, they are just given by Heaviside thetas, so also simple. And the W, which I use for the deformation, is a logarithm of something. There is some mysterious epsilon here, which means that, well, there is a distribution, I have to take some limit, blah, blah. But mainly, you have to think of it, hey, there is a logarithm. Why is it good that there is a logarithm? Because they're exponentials, and exponentials of logarithms are powers. So everything can be really very explicit, and also one actually can prove something. Right, observables. So observables which we want to use in this are essentially vertex operators and their combinations. And as I said, for me, observables are just some functionals. So here, well, very naively, classically, you would define the vertex operator just by exponentiating a field and integrating with some test function. Why not? And note that I haven't mentioned Hilbert spaces, no states yet, so everything is just algebra. And with that, one can already show that the commutation relations of such objects using the Moyal formula are exactly the commutation relations which you would expect for vertex operators. So there is a chance we are not doing something completely wrong. Okay, but we do have to choose a state. So for me, what's the state? Well, it's some functional unobservables, which has to be positive, somehow related to probabilities and things, and these tend to be positive, and normalized. Okay, so, right, but there are many states. I mean, if you were growing up with operator algebras, you'd realize that, okay, there are plenty of states. So, in 2 dimensions, for massless scalar field, there is a problem with the vacuum state, but there's a huge class of beautiful states called Hadamard states, which are there, so why not use them? So this is what we did. So we didn't worry about the vacuum, we just used the Hadamard state, and this essentially means, okay, so this mysterious W, which I introduced before, is just a 2-point function of a chosen state in the end, and the choice of the concrete Hadamard state is just the choice of H. And these differ by smooth functions, so that's maybe not so important. What's important is that the products you get for different choices of these H are all equivalent. And they are equivalent in the very precise sense, so there is an operator, there is an isomorphism which is explicitly given by another exponential, and in the language of Kontsevich deformation, this is a gauge transformation. The name gauge is probably very misleading, but that's how it's called. So, okay, we make a choice, but this choice doesn't matter, so that's the bottom line. And for physicists, this choice would correspond to the choice of normal ordering, so the 2 dots. Okay, so we can use that to write expectation value in that given state as evaluating our functionals at 0. So there is a very simple way of transferring your abstract algebraic formulae into concrete numbers. Okay, so that's what we can do also for the S matrix itself. So the only thing which we have to show is that this time-ordered exponential here, that S matrix, actually makes sense. So we know that it makes sense as a formal power series, but you can ask yourself, fine, but does it exist? Like, you know, operator on Hilbert spaces and things. And this was actually, well, was surprising how easy it was. So we proved that result in our paper, which appeared last year on the archive and hopefully soon will be published. So that's the result. The formal S matrix defined in this framework for so the coupling constant sufficiently small. So in the regime where you don't need renormalization, we showed that this makes sense as a functional on the configuration space. And using the formula for the interacting fields, we actually can define the local net of observables. So there is something positive coming out of it. Right, so what's good about it, it's a direct proof in Minkowski's signature. So now the big rotation, it's very explicit. In principle, you could do it on curve spacetime, but okay, in 2 dimensions is maybe not so exciting. Yeah, so as I said, works without any further problems. And another thing, it is independent on the choice of the state. Okay, so these are the local observables. I haven't written them down because that would take some time, but these have very explicit formulae. Okay, I will skip the outlook because I'm running out of time, but just maybe very quickly. So we want to extend the results to some other regimes where you need renormalization. We want to construct something like the interacting vacuum, although we were avoiding the vacuum topic for now. And yeah, I mean, go on and quantize, so apply it to more models and show some dualities in that framework as well. Right, so thank you very much for bearing with me.